First of all, thank you, Angie, for the opportunity to talk to a great bunch of people who really want to learn about these things. And it's so great that you and Monadic is doing these kind of stuff. It is really amazing. I really hope something like this exists here in India. We don't have any such thing here. And I would love to participate in any such thing here, but unfortunately, maybe I have to talk to more people and try to get this kind of thing going by myself. But yeah, this is really great stuff to build a community, especially around a topic like P2P, which is becoming really, really important in the coming days. My name is Ram. I work for a company called Lease Authority, which is based in Berlin. I work remotely. Most of our employees, we are a small company, just about 10 or 12 people. We are all mostly working remotely, but there are four or five people in Berlin doing various things. Our CEO, the founder, is also in Berlin. Liz, she'll be talking to you as well. We mostly are a bunch of people who are really concerned about privacy. I'm not sure whether you've heard of this project called Tahoe LAFS. So there is this very old, about 10-year-old project, free open source project by name Tahoe LAFS, Leased Authority File System. So that is from where we are getting our name, Leased Authority. It was found by a person by name Zuko Wilcox. So he, probably you may know him from the Zcash project, which is a very privacy-oriented cryptocurrency where transactions it's a private cash-like version of a cryptocurrency, cash-like Bitcoin, you can say. With a lot of very nice and cool properties. So he found this company before he found Zcash to make a commercial offering for Tahoe LAFS, where people can store their files, and files are encrypted from the client side itself. That is, file does not leave your computer without getting encrypted. Unlike a service like Dropbox or Google Drive, where the service provider can read the files and delete them and do whatever they like. So this is like a completely encrypted file system, which is like completely client-side encrypted. And it has a lot of cool ideas, and a lot of other projects are picking it up and using some of these ideas, which is really nice. We also really want others to use these ideas and build other things. Need not necessarily be Tahoe itself, but just other cool things around it, because there are quite a lot of ideas, very nice ideas. Like, for example, the something called object capabilities. Just a short intro about object capabilities is that, let's say you have a file copy program, just a Unix CP program. The Unix CP program has all the permission it wants. Like, it can even access the network and nobody is going to complain, even though its job is to just copy files. But in reality, it should only have capability to read and write files in a particular directory. But in reality, it has permission to do anything. It can access cameras, it can access anything it wants. So object capability is a way to just give only the permission a program needs or a person needs. So I could pass a capability to you and to view a file, but not modify it, for example, like view some photos but not add any photos into a directory, or I could give you a permission to write and edit them. So that kind of stuff, like a very fine-grained permission system, all using cryptography. So that's so we have this commercial product around it, and we also do a security consulting, like code audit and all that stuff. So yeah, I mostly work on the audit side of things. I also do a little bit on the file system part as well. So the motivation for this talk came from another project I worked on called Magic Wormhole, which is a way to securely send files from one user to another. So right now, sending files from one person to another is a really difficult task. You may email it from to your own, say if you want to copy from your phone to your computer, um, you may sometimes email it. You may want to connect your USB cable or SSH or all sort of things. Whereas it should be simple. It's 2019 and we still are doing all these kind of things to just copy files with your own computers, or say share it with your friends or your family. It's so hard. And let's say you're sitting next to somebody and you want to share some files. uh, it's really hard. Let's say you go to a conference and you want to share some files with somebody sitting next to you, and that person is a stranger to you who you just met at that place, and you want to share something. It's so hard. So there is this person by name Brian Warner who earlier worked with the Tahoe project. He came up with this really nice idea called Magic Wormhole. It's a very nice protocol to copy files from one place to another. Uh, it does not need to know usernames or IP address or any such thing. All you need to know is a small code, English code that can be pronounced via a phone or via some other channel like an instant messenger like Keybase or something. And the other person can just type that in and get the file. And so I worked on that project, and one of the issues that I'm looking at for that is to um, how the people on both the sides. So there is also this, if they cannot discover each other for some reason, um, how will they copy files? So that we have something in place for that now. We'll discuss that in the slides. But copying it to another server somewhere on the internet and then copying it to the recipient seems very inefficient and probably insecure as well. So I just want to get rid of that. And that's how I started researching about this topic more. And there are a lot of cool things we can do. And there are many other projects which has similar problems, including things like Bitcoin or any voice over IP program. Even the Zoom Messenger, for example, may have similar problems, like a one-to-one talk. Instead of going through their server, it's probably better to talk directly, send streams directly. It's much more efficient for everybody. So that's when this topic comes in. Please interrupt me if you have any questions at any point, right then and there, because we don't want to lose the context. And my goal today is that you all go back with good knowledge about what we are discussing today, and give you enough tools to read and understand about this yourself and read further topics. And you can, if not today, you can always reach out to me at any point of time, and I'll be always happy to answer about this or any other questions that you may have. So I will try to share the screen. Okay. You're seeing this now, right? Okay, yeah, thanks. So I'm also on Mastodon, which is another decentralized social network platform, which is, if you have not heard about it, it's really cool. It has a lot of very nice ideas in there, like federation and all that. We'll briefly touch about that. Okay, yeah. So so modern internet, yeah, I have a typo in there, sorry. So modern internet, if you see, they are mostly around centralized services like Google, Twitter, Facebook, or anything you take. They are like completely centralized now. Even email, for example, almost everybody is on Gmail. Many of the young people, if you talk to them, they don't even know that there is email exists outside Gmail, that you can have a email ID with anything other than gmail.com, because their idea of internet is just completely around certain centralized services. They live inside Instagram and Facebook, and it's like completely walled garden, as the people talk about. Like you are living in a completely walled place. Inside it's so nice and you have friends and other people, but there is a big huge internet out there that people don't know about. That's this first diagram in here. Now the second diagram is the decentralized internet. By the way, this diagram is from a paper uh, which was published sometime in the early 1970s. So this, from the diagram, you can make out, from the print of the screenshot, you can make out that this is like a scanned diagram of a printed cyclostyle paper. So it's like a really old concept, which now you can see in many of the decentralized conferences or talks you go, you will see this diagram being used. But this is really from a 1970s paper. So the second one, the middle one here, is the decentralized internet, where you have these centralized nodes, but there are many of those centralized nodes, and they talk to each other and they provide services to each other. To give you an example, the internet relay chat, the original internet relay chat, which still is very strong and a lot of people use it, mostly by technical people, sadly, because the UX is so hard and so people have, now there are quite a lot of UX being developed around IRC, but for so long that has been a neglected area. That's one big challenge facing the privacy area and the P2P, by the way, the UX. There are so many nice ideas in here, but the UX is really lacking at this point. And that's one thing that a lot of creative people like you may want to work on. And there are a lot of challenges there. So this is the decentralized web. So the Usenet, the original Usenet protocol also was somewhat like this, that you had this NNTP servers, people post news articles. That was like somewhat like mailing lists. For example, you had you can post articles into a Usenet server that you subscribe to, and there are many Usenet servers, and they all talk to each other without you knowing. So there is a server-to-server protocol, and even Mastodon, for example, is like this. You can have many Twitter-like servers. So Mastodon is like a Twitter-like service, and you can have your own instance running, and around that instance there are many computers talking to it, and then you have another Mastodon instance, and there is a server-to-server protocol. You can talk to other users on the other server. Email is a classic example. Like I can send email from my domain ram@rkrishnan.org to Angie another domain, for example, monadic.xyz. So, and that perfectly works. Not all users need to be in one centralized service. Then you have the distributed service where the individual nodes, these small dots here, they all talk to each other, and anybody can talk to each other. So this kind of thing is sort of Bitcoin is somewhat like this. There are Bitcoin nodes. People can run Bitcoin nodes all over the place and on their own machines, and they all talk to each other. BitTorrent, for example, is sort of somewhat like this. Yeah, so there are many such things. Any questions about this? This is just setting the stage for further discussion. So if you have any questions, please interrupt me. Okay, I'll just move on to the next slide. Okay, so again, so this is the map of the original internet. There are just very few nodes across the United States alone, and then one of the first nodes outside the United States was in the London University College in London, I think. Web was like a completely decentralized place. It was designed to be a decentralized place, and most of the protocols were designed to be completely run in a decentralized manner. So explicitly, like email, the chat, the Usenet, to name a few of them, but all of them were designed to be completely decentralized. And this was like before TCP/IP. There were some other protocols like Network Control Protocol. I think it is called NCP, which is a precursor to the TCP. The internet was so small that they could just they could have a flag day of shutting down internet for one day and say that, oh, tomorrow onwards we are going to use a new protocol, TCP/IP, and tomorrow onwards everybody is going to use TCP. Imagine doing that today, shutting down TCP and just using another protocol. It's just not possible because it's so big that it's so hard to switch protocols like that.
A quick question, Ram.
Yes.
So did you say decentralized and not distributed? Is that on purpose? When it comes to the original intentions around the structure of the internet?
Yes, it was more of a decentralized, this kind of a network. The middle, the B, this kind of a network it was, rather than this kind of a network. Because at least at that point of time, they really wanted some sort of federation to work. That is, people could run their own services on their machines and share the resources. So I think not everyone had the resources to run their own services like this. Like the part C, where each of them are running their own service and everybody is using them. Neither did they have enough reliability of the network at that point.
Got it. That's really helpful. Thank you.
Yeah, thanks. So when I say nodes, to clarify, nodes are not really computers themselves, but somewhat like the today's equivalent of a home router or an organization router that you have. And then you have host. This is a terminology you may see in some of the early internet documents. So there is this concept of request for comments. So people, when they, their Department of Defense, when they started doing this ARPANET, the precursor to the internet, somebody took notes of meetings that they hold and they just published it and wrote it as request for comments. So that's how the RFC thing started. And now you have RFC document for every major protocol, so nicely documented with ASCII diagrams and everything. But it originally started as a somebody just took notes of meetings and just sent it out and published it for everybody else to read. And so wonderful, small community of people developing this. It must have been a really nice time to be around in these places at that time. But yeah, it's still, we are able to use this, and yeah, this is wonderful too. And because of this, we are able to have this kind of a call. Just imagine we are sitting in two totally different parts of the globe, and we are all in different places, and it's just really, really wonderful. And these people are really, they had a lot of foresight to design these in a futuristic way, the protocols to work in many different types of situations, like error handling, packet loss. So that there are various types of protocols to handle all these kind of things. Like you have the TCP and the UDP, and there are many other protocols. And the layered architecture, they are also nicely designed. And over various types of links, it works from radio links over the RF to high-speed links, and to this day. And there are still changes being proposed and improved upon on all these things.
And can you just quickly say something about, I guess, these different protocols, and especially in the early days, I mean, what did well, I don't want to derail the conversation too much, but why so many different protocols? Why were they created differently?
So initially there was no TCP or UDP or anything. It was just one protocol called NCP, and there was not even a layered architecture. So they, I think the layered architecture is sort of a way to separate different concerns. So you have one layer, it's like a different layers of abstraction. So the lowest layer is like dealing with hardware and concerning about the link quality and hardware things, like sending, oh, I sent this packet and there was a packet collision somewhere on the wire. Now the other person did not get that packet. Now I need to wait for some random amount of time and send it again. So that layer dealt with that. Now there is another layer on top of that that dealt with other things, like, oh, there is this concept of a source address and a destination address, that I need to have some sort of ways to give a address to the different hosts. So how do I do that? Now there's another layer developed on top of it, like how do I use this sort of way to deliver packets to send email, for example, like how do I build applications on top of it? So now each of these needs to have some sort of a very well written protocol so that other people can implement them and interop with them. So and TCP and UDP again is because TCP is a connection oriented protocol. What that means is, like, you create a connection and you don't have to worry about the order of the packets. That you can think of it as a pipe where you could just send packets, even though there are multiple ways a packet can reach from a source to a destination. Packets may arrive out of order. Like first packet may come as a second or third on the destination, but it doesn't matter for most of the applications, except for real-time applications like the video conferencing or voice telephony and things like that. For most of the application, it does not matter. So then you assemble them in order, and for the missing packets, you say that, oh, I didn't get these packets, so please send them over to me. So the TCP does all that behind the scenes, whereas the UDP is like a more lightweight version where the application has to take care of ordering and out of like out of order or missing packets or packet loss or errors in the packet, making sure that packets are really, the integrity is fine and things like that. Otherwise, so some applications like voice, they don't want TCP for voice calls or video calls. They just build on top of UDP. It's much easier, whereas TCP has a lot of other overhead and rate control, and the connection establishment takes there is a round trip. First it sends something, there is a three-way handshake, and all that has to happen. So different applications have different requirements. So that's the reason why so many protocols have come up.
Thanks, Ram.
I hope that clarifies.
Yeah, definitely. Thank you.
Thank you. Yeah, thanks. So right now it's like so the internet completely exploded after email, and email was one of the real killer applications, and then the World Wide Web started. The browsers came, and the World Wide Web was invented, the hyperlinks, and that kind of put internet out from the scientific community into the rest of the world, and people started building all sort of applications around it. And so just to, you may know all these concepts, but just to set the stage, after the World Wide Web became very popular, the browser became the most dominant application that accessed the internet. And what that really means is that you mostly have clients running on the computers and not much of servers. So most of the computers on the internet are right now clients, and they're not providing any service. There are like few centralized computers providing service. The number of the number of hosts or computers providing services is much lesser than the number of computers just using those services. So the ones that are using these are broadly called clients, and the ones that are sort of providing services, they are called servers. So if you want to be on the, if you want to put a computer on the internet, when I say computer, nowadays it is mostly almost everything, including doorbells and whatnot, everything. Like people have all sort of things, like you have this Internet of Things movement, right, where people have thermostats and even internet connected switches and lights and all sort of things. Now, all of them need to have some sort of IP stack on them. Like you need to have some data link layer and an IP layer. There needs to be some software in there to run the network processing, packet processing. And the bare minimum, you need to have every device on the internet needs to have an IP address, which is a 32-bit field on the IP header of the IP packet. And it is sort of represented like this, like A.B.C.D, like 192.168.1.100. It is arranged in an 8-bit. So 32 bits is split into 8-bit fashion and represented like this. And so as the use of these kind of devices exploded, what happened was these 32-bit addresses were starting to run out, and we have like close to 3.2 million addresses. So there are if there are like 32-bit field is like 4 gigab. It's like some huge number of addresses, but many of them are like multicast addresses and so on. So they cannot really be used to assign to a device. So broadly, there are about 3.2 million addresses. So they started to run out towards like 4 years ago. And people started thinking about this like about 10, 12 years ago itself, that, oh, we are soon going to run out of this address and what are we going to do? So they came up with two solutions, broadly two solutions. So one of them is based on the assumption that most of the computers are just acting as clients. We are just browsers accessing the internet. So why not create a sort of a private IP address range in this 3.2 million address space and reuse those private addresses. Like, for example, I have a home router here, and I have like 5 or 6 different devices here, a couple of phones and a couple of computers. Let them all have share a range of private address. Another house just behind this house, they have got their own router, and they need not be using different addresses. They can also use same addresses, for example, because they are on another home router, and they have like a bunch of computers at their house. And similarly, you have offices. They have a bunch of offices having hundreds of machines. They don't really talk to other. They can just share a bunch of private address space. And so similarly, most of the computers are like client computers, and they don't really be on the internet. So the ones that really have to be assigned a real IP address, the public IP address, which is among these 3.2 million addresses, are the ones that are really talking to other computers on the internet and routing these packets to the external world. Somewhere there are like multiple hops that a packet has to take to reach its destination. So only those routers which talk to other gateways needs to be having these public IP addresses. So that is one scheme that people came with. And the other scheme is the IPv6. So what we are discussing now, the 32-bit IP address, is called the IPv4, and the other scheme is called the IPv6 address, and that is like a 128-bit address, which is really, really, really big, and it is represented like this, like a group, 8 group. It's grouped in 8 blocks like this, separated with colon here. Like these are represented in hexadecimal numbers here. But there is the biggest problem right now is that even though IPv6 standards are out, they just don't talk to each other. There are a lot of incompatibilities, and all the routers in the world needs to be upgraded to talk to other IPv6 addresses, and that unfortunately has not happened. It's happening very slowly, but once it becomes popular, then we won't have any problem addressing any number of devices on the internet. 128-bit address is like really, really big. It can address, for many years to come, it can just work without any upgradation. So I think 128, 2 raised to 2 power 128 is like some insanely high number. So maybe much more than number of atoms in the world, perhaps. So it's like, yeah, it's not going to run out. So the other solution, the previous solution that we discussed, the private IP address system, is called the network address translation, that we are going to discuss in more detail now. That got specified in these RFCs that we talked about earlier. These two are the RFCs that first proposed this idea of RFCs, that you can translate a single public address into multiple private address. That's the whole idea, and we'll discuss that now in more detail. Any questions so far?
If no one's going to ask something, then I'll ask something, which is, again, since we're talking, we're going to be focused on NATs. I just want a little clarification on the IPv6 and the future. I mean, ultimately, are we headed in that direction? And is it what needs to happen in order for that to be successful? Do all IPv4 addresses or anything that holds an IPv4 address today need to switch to an IPv6?
So right now, almost every modern computer is capable of doing IPv6 addressing. It's just that the ISPs have to upgrade their architecture. So ISPs, the internet service providers, have invested a lot of money into their infrastructure, and they don't want to just throw them away. So some of the newer ISPs, for example, are investing into IPv6. So from what I've heard, quite a lot of ISPs in the Europe and the US have IPv6 addressing available. You just have to enable them and just ask for them and just configure it on your machines. Linux and Windows and Mac OS, they all support IPv6 out of the box for many, many years now, and very mature. It's really mature. So I think it's mainly the ISPs and most of the router companies like Cisco and those kind of companies, they also support them. And companies like Google, Microsoft, and Facebook, they use IPv6 internally in their data center. And they all have been using IPv6 for many years now. So many large organizations, they use IPv6. Cisco used to use IPv6 internally. I worked there for some years. So they used to use IPv6 internally as well for their internal computers. So I think what really needs to happen is the ISPs in many other parts of the world, probably not in developed countries in Europe, but in other developing countries. For example, I get IPv4 address here. I don't get an IPv6 address at all. But one of the newer ISPs that has come up is giving out IPv6 address, which is really nice. So with that, I think you are completely on the internet. You may go through some filtering maybe at the ISP side, but you get a public IP address. So that's really nice.
Got it. Thank you.
In what ways does IPv6 not operate with IPv4? Or will we touch on that later?
No, we are not touching on that much later. We are mostly talking about IPv4 here because it's going to be around for a long time. So mainly these the IPv4 infrastructure and the IPv6 infrastructure that companies maintain are sort of separate. So the MAC addresses have no problem, but there are still let's say source address is IPv4 and destination address is IPv6. Now that's not supported now. So yeah, those kind of problems. So there are IPv6 packets have to be IPv6 alone, IPv6 on both the sides, because I don't think they support sending packets from one to another. And there are, I think there are solutions to that, but there are infrastructure problems as well. There are routers that may decide on how to send them in their own way. Some of the earlier implementations that came out didn't have a proper way to route packets among these two networks. So they did their own custom stuff. Even in NAT as well, we are plagued by those kind of problems. We'll discuss about later on. Yeah,
cool.
so those
Thanks.
are, yeah, thanks. So network address translation, one nice analogy to think about is an office telephone system. Like sometimes office is not able to provide a reachable phone number to each of the person in the office. So what they do is they have one public phone number, and each of the desks have an internal extension number. So while these phones can ring to the outside world, say with a zero, pressing 0 or something, or 9 or something, then they can reach out to any number in the external world. An external phone cannot reach an internal number so easily. They'll have to first dial one public number, and then there'll be some sort of a interactive voice response system that says, please dial the extension number that you want to reach, or pass it to an operator or something, and then the operator routes you manually to the particular phone number. So NAT is somewhat like that. So you have a bunch of internal networks, like a home network here, there is another home network here. Each of these home NATs are like your home router sort of acts as a NAT, and then you have the ISPs. The ISP itself may be running another NAT, so they may be really huge, and they may not have enough public IP addresses to give to each of these routers. They may be a small time ISP. For example, my ISP does not give a public IP address to my router. They give another NAT address to these routers, another private address to these routers. And then there is another layer sometimes of another bigger router, like a carrier grade sort of a router, and that connects to the main internet. Or there could be a smaller network where the home router directly gets a public IP address, and that routes it. So I think in many of the cases, it may be this. My previous ISP was this kind of a network, the one on the right. But unfortunately, my current ISP is somewhat like this. More levels here is always more problems, because each of them can behave in different ways. So this is probably the best of all the solutions. But this is how the topology is. Most of the networks would look somewhat like this. And then you have these. So all these are like edge computing devices, like phones or laptops or tablets or another IoT device and those kind of things, like a phone and those kind of things. And they all have private IP addresses. It could be either 192.168, that range of addresses. You might want to look up your address in Unix command line. You can check that if you have a Unix machine, or even on Windows. I think there are some command line options. I don't know the exact Windows command for that, but on Linux, you have this ifconfig command that can tell you what your IP address is. There may also be graphical interfaces to know the IP addresses, but from the command line, that's what you can run, the ifconfig command. And you can see the IP addresses. Most of the time, it will be some private IP address. At a bigger layer like this, at another layer of the NAT, it could be 10.0.0. something, that kind of address. That's also a private IP address. So the IP addresses, you have different classes of IP address. You have class A, class B, and class C. Those are like 3 different types of addresses that people came with, which are independent of NAT. That is like 3 different classes. So large organizations can use class A address, sort of medium organizations can use class B address, and smaller organizations and smaller ISPs, they can use class C address. They all are about how much IP addresses that you get. So these 4 octets that we talked about here, that A.B.C.D, this is where the class A, B, and C would differ. So the class C address would only change this part. Anyway, it doesn't matter for this discussion much. I think even if you didn't really understand this, please don't worry about it. It doesn't really matter. You can just read about it. It's really simple concept of different classes.
Quick question.
For this, yeah, sure.
You mentioned about like the more layers of NATs you have, in this picture, the more problems you have. Can you just can you be more specific as to like what kind of problems you would experience?
I'm talking about some of them later in more detail.
Okay, then we can wait.
I think that is where it will make more sense after we discuss some of them. So just 2-3 slides later, I think I'll be talking about that. Okay, thanks. Any other questions before we move to the next one? Okay. So one thing is the computers on this have some IP addresses like 192.168.1.100. Computers on this network may also have 192.168.1.100. So how do we talk to them? This sort of breaks. So computers on 2 different private networks just cannot talk to each other. So think about a P2P case where you want to run a service on this home network and your friend wants to run another service on this network, like a web server, for example. Now, how do you talk to each other? If I just give you my IP address 192.168.1.100, it would just make no sense on your network, because you may have another address 192.168.1.200 and 192.168.1.100 may be another computer on your office, and that may not. That's like completely different computer, and these addresses they have any meaning only within that private network. So this sort of completely breaks the idea of running P2P services and like providing peer-to-peer service. Think about the file transfer application that I talked to you about initially. Like I'm sending a file to you and you are on a different private network. How do I even identify you, and how do I send it to you? It's so hard. So that's why we have ways to break the system and try to. So this works in practice because most of the computers are just sending files out there. They're outward connections. Like connections are always outward. So in that case, there is no problem. Like I'm accessing, say, google.com or zoom.us. Absolutely no problem, because zoom.us is sitting somewhere on the internet. These packets are just going to go out and access some public IP address. Absolutely no problem. Problem is when a zoom.us like service is hosted on one of these private networks, then you have a problem. You just cannot access them at all. So in that case, you need an inward connection into this NAT router, which it won't allow because it simply doesn't know. From my network, if I say, oh, go to 192.168.1.100, it simply doesn't know that I'm asking about this machine. I'm actually talking, it would think of a address in this network rather than this network. So that is the problem we are trying to solve here. So this is how we try to solve it. So there is this concept of a session that each of the router maintains, and that's called the source IP and the destination IP. So every packet that I send out, and the IP packet, there is a source IP address and a source port, and a destination IP address and a destination port. Port is nothing but a 16-bit number, and IP address we talked about, it's a 32-bit number that identifies a device. And port helps you identify a service running within a computer. So each service, like a web service, will get a number, whereas email will get another number, and some other service that you run may get another number. So these are all ports which are serving other users. So most of the time, the listening port or the destination port is what matters. The sending port is usually some random number, whereas a destination port is a well-known number. For example, a web server runs on port 80, and there are other well-known ports. You have Telnet runs on 21, and there are SSH runs on 29, I think, or 23, I forget. Yeah, there are various ports like that. And IRC runs on its own port. So there are many such well-known ports. So that's the concept of a port. So what the router does in this case, when a packet goes out here, when you try to access, say, google.com, what happens is the packet here will have a source address of this device's source address, which is some private address and some port. And then when it hits the router, what it does is it will make a table entry like this. It will make an entry, source IP of 192.168.1.100, and some random port is trying to access google.com's IP address and the port 80. So it will make a note of that. And what it does is it will rewrite the packet. It will take the packet, it will go and access the source address part of the packet, and it will put its own IP address and possibly its own port into that packet. So the packet that leaves the NAT, let's take this part rather than this one, because this has multiple levels. Let's take this one for this discussion because it's much simpler. So it will take, this NAT is going to take this packet and it's going to rewrite the source address and the source port so that the packet which is leaving this particular link into the internet is going to look as if the router is sending the packet, not this computer which is sending the packet. So when the google.com or whichever computer receives the packet for google.com, gets this packet, it will respond back to the source address that it sees, which is the home NAT machine's source address. So it will put the destination address of the return packet as the source address that we sent out, which is the router's source address. And then when it receives the packet with that particular source address, it's going to look up its table that it created. So it sort of created a table here, the session data, and says that, I sent a packet out on behalf of this private node. Now, so it rewrites, it puts the source address back to the sender's original packet, the destination address of this particular computer's IP address, and sends it out on this link, and I receive it. So my computer has no idea that the packet got rewritten and it got sent out and it went to google.com as if it was sort of masqueraded as coming from this particular computer all that is abstracted out. So it's like a very nice system. If you're just accessing the internet, it solves the previous problem of IP addresses running out. All of us get private IP addresses. It's sort of transparently handled by all the infrastructure which has already been put in place. The home routers and the ISP level routers, they all handle this. Any questions on this? Because I think we didn't have a lot of diagrams and we sort of talked about this. So very likely that some of you may not have completely understood what this concept is. If you didn't understand, we can go through this once again.
For me, it was clear. What will make it even clearer is understanding where it doesn't work.
Okay, yeah. Any other questions? Okay, now we'll talk about why it doesn't work, Angie's question. Question is this, what if I am accessing instead of this google.com, I'm accessing a service running on this particular machine. Now, how do I advertise that I have a service running on this machine? And how do I, as a client or the user of that service, am even going to use that service? First of all, the address would just not make sense at all, because this also will share the same namespace of private IP addresses. Like it will say that, oh, I am running on 192.168.1.100 or 1.500, 1.200 or something, and you only have numbers from 0 to 255 because we are talking about 8-bit numbers here. So 192.168.1.200, let's say, is the IP address of one of these machines. But this network itself may have one of those private IP addresses. So if you're providing some sort of P2P services, so let's say you have a computer on the internet directly. So these are not behind NAT. These are directly on the internet. How do I talk to a computer which is behind the NAT on one of these machines? Only these machines are reachable on the internet. So if I send a packet from here to 192.168.1.100, that route just does not exist. So some of these routers here itself may drop it. It won't even travel anywhere. It would not even survive the first hop on the internet. The first hop itself is going to find that, oh, there is no way that I can route this packet, because it just doesn't know how to route it. So it's just going to drop it there. Is that more clear now, Angie? Okay, thank you. Yes. So NAT is a way to make a session outbound. So outbound packets have no problem. So things which are accessing network outbound has absolutely no problem. Whereas things which are inbound, this NAT server has no way to identify that if a packet arrives here, who should I give this for? It has no idea. It would just drop it right here. So that packet would never reach anywhere inside. So that's where the problem is. And that's something we may want to solve. So one of the ways it can solve is via an external relay server. Say, like for example, the file transfer program we talked about. Let's say that I'm sending it from this network to this network. One way you could do is to have a central computer here and transfer it into that machine, which is reachable by both of these. And so this machine also makes an outward request to this relay server. And so both of them talk to this outward connections and copy this. So this is going to copy it into this machine, and this machine is going to read it back it makes a request out, say that, oh, I wish to copy this, and then reads it back into this machine. Both of them are outward connections, and then it reads back. So that is one possibility to solve this problem, but having relays is very inefficient. It consumes a lot of resources, and you need copies, direct talking directly to machines is always better and more efficient than talking to another third party which you don't know about. You don't really trust that third party. For example, you should really never trust a central third party, for example, and then copy it there, especially if you don't use encryption. You are totally at the mercy of this third party to either turn that machine off or all sort of things. So it may just disappear while you're transferring file, and you have all sort of reliability issues. And so talk as far as possible in a more decentralized world, our wish is to directly talk to the peer rather than use a third party. So that means that we should minimize, one of our goals for the NAT is to minimize the use of an external relay server. So that's what we want to explore. So for that, there are a few, before we discuss ways to, so there is this technique called NAT hole punching, that is putting a hole into the NAT so that people can discover each other. That's what we are going to discuss. So before that, we are going to discuss various types of NAT. So we talked about the session data, that is source IP and source address, and destination IP and destination address. And what this router does, that is, it creates a table whenever it sees an outward packet. And then when an inward packet comes from this particular address that this machine sent out, is going to find a match for in that table, and if there is a match, it is going to route to this machine. Now, the problem is that how the mapping is done is not standardized by any RFCs. It is left to the implementers of various NAT routers to decide how they want to do it. And that is the source of all problems. And broadly, there are 4 ways in which people have implemented that, and that's what we are going to discuss next. But before that, if you have any questions, we can go through that. I hope these things are making sense. They're not like too technical or too low in your expertise, or whether it's a right level of technicality that we are going through, or is it like too hard to understand or too easy? Please let me know.
Thanks, Ron. I mean, from my side, I'm feeling good about it, but I will also encourage everyone to reach out to you via Keybase too, if they want to dig deeper
Yeah, sure.
and maybe go more technical.
Sure, yeah, okay. So now one of the first variant is called a full cone NAT. So remember, we talked about this. So this is the thing you need to remember. Every outward packet is going to have a source address and a source port. And there'll be a destination address and a destination port. Now that's called a session data. This pair of IP address and source IP and port, and the pair of destination IP and port. And also the other other terminology you might want to remember is these are called private IP and port pair, and what then this particular machine provides is a public IP and port pair. So that's something we'll be talking about again and again. So there is this thing called full cone NAT. I don't know why the name cone here. don't really know about that, but the concept is very simple. It's like a very simple NAT that can be easily circumvent. So what here happens is that, let's say you have a private network here, you are behind some router here. Now there is another machine on the internet. Now this computer has an internal address and internal port, and the NAT machine, the NAT router here has mapped it to an external address and a port, because you sent out some packet here first. So it mapped that port. Now this external host can talk to this internal host, no problem, because it has already, the first initiation of the communication came from the computer inside. So now this computer can, which is outside the network, can talk to the machine inside. Absolutely no problem. Now let's say there is another computer here that wants to initiate a communication to the internal computer here. Remember that it's an initiation of a conversation and not, this machine is not initiating it. The arrow is towards inside. That is, this is sending a packet to the public IP address, which is this router's public IP address. Now, what would a NAT router do is the question. So in the case where the NAT router has implemented the full cone NAT, any external host for which the session mapping is already created for can send packets to internal IP and internal port by sending it to the destination address. That is any external host, not just the one for which this mapping has been created for. So in this case, this is the host for which the mapping exists. But in the case of a full cone NAT, even another machine can just send a packet to the external address and external host address, external address and external port, and that would also get routed to the service which is running on this particular machine, which is a really simple case, and there are very few routers that really implement it, making our life so difficult. So, but had it been this way, things would have been really, really simple. This has got some other problems like security, for example. Anybody can send packets to the internal computers. So somebody could just bombard this particular router with packets and cause denial of service, for example. So there are all sorts of problems that this can have. So because for that reason, this is not very popular. Anything at this point? This is clear, this particular slide? Okay, I'll move on. So the second variant is called the address restricted cone NAT. Now, from this discussion, you know that anybody could send packet once this session has been added, once one particular machine has punched a hole here, anybody can use that hole and send a packet to this machine internally. Now, that is slightly different here. So here in this case, an external host can send packets to an internal host provided the address match. So this particular machine can send more packets to any other port also on this machine, not just the same port that opened this hole. So the hole that got opened was because of port 2000, which means that there is a listening service listening on the 2000 port, whereas there may be other services running on other ports. For example, port 80 may be running here. Now, in the case of address restricted NAT, this particular host for which the hole has been punched can also talk to port 80. Whereas another machine here cannot talk to any of the services. It cannot talk to service running on 2000 or 80 because the address does not match. The external address of this machine is different from this machine. So the table entry here does not match, and so this is going to drop those packets which are coming here. So whereas for this particular machine can send a packet to any of the ports running here, to any of the services, and that would just work. That's what is called an address restricted core NAT. Any questions? Okay, I'll move on to the next one. So this is like, you can see where this is going. So now the next variant is a much more restricted version of this. So you have, in the previous case, you have an internal address talking to an external service. So a hole is punched here, a table entry is made in the router. Now this external host can talk to this particular service running here in port 2000. But it cannot talk to any other service running on this machine itself. The same host for which we punched a hole cannot talk to even other services running on the same internal machine, because this router is going to also look at the port number coming from this particular machine. So it is going to look at both IP address and the port number. And if that does not match, if both of them do not match, it's just going to drop it. So this machine is ruled out because this machine has a different IP address. So even if this is talking to this particular port, it's going to drop it. If it is going to talk to another service running on this machine, again, it's going to drop it. This machine itself, if it is talking to 2000, then it's going to accept that. It's going to accept those packets. But if it is going to talk to another service here, like another port, like say 3000 port, it's going to drop it. So both the IP address and the port has to match. So this is like really restricted. And so you punch hole only for one purpose. If you want to talk to another machine, you have to punch another hole, which is like another entry on the table. The router has to make another entry on the table. Is that clear? Okay, I'll take that as something clear. And again, as Angie said, please reach out if anything is not clear. I'll provide another couple of other references on the Keybase channel for you to read more about, a few more references so that you can read them about. So now this is called a symmetric NAT, and this is the most complicated one for which the solutions do not exist to punch a hole even now. And this is very prevalent in corporate enterprise routers like Cisco home routers. This is very common, and it's really one of the #1 enemies for P2P applications. So what here happens is that just as in the previous case, you punched a hole here. You sent a packet to port number 2000, and that worked, and you created a hole here. Now, the same internal host sent a packet even to the same source address and port, but to a different destination. That is, the same internal address, the same internal host sends a packet even with the same source address and port to a different destination. That is like to a different port, so the source address and source port is the same, but it sent a packet to a different port on this machine. It's just not going to allow it. Similarly, so what really happens is this particular NAT router, when a packet leaves this network, it's going to assign a different, it's going to assign a new IP address and a port, and it's going to rewrite that. In the case of symmetric NAT, it's going to assign a random port number to each of these different connections that is going out. So that's going to create some problems, which we'll see now later in the next few slides. So it's going to just allocate a random port. So let's say you want to discover what's the internal port that is running here using an external server, for example. That's just not going to happen, because it's going to use one port for that connection. If you access another computer, it's going to use another port number here. It's going to assign, even though this port number may be same, the port number that is allocated here on the outgoing packets here are going to be different. So that's going to break most of the assumptions about sending packets back and creating a hole here. Yeah, this is a bit confusing. So if you didn't get this part, please don't worry about it. It takes a bit of time to get this. So the main complication here is that in the regular case, the router here is going to rewrite the source address and the source port to a new source address and a source port for the outgoing packets from here for this link. Now, most of the time, the port numbers are kept the same as this port number, whereas for the symmetric NAT, the port number is going to be different. It's going to assign a random number into this port number, whereas for this connection, it's going to assign a different random port number. So let's say you try to find, let's say you're running a service externally to find, oh, what is my, tell me what is my IP address and a port number. That server is going to respond with this, the source IP, the public IP address and port number that this router allocates. But now you can't pass that public IP and port number to another computer and say that, oh, please use this IP address and port number to send a packet to me, because it is going to match both the IP address and port number of the sending node, and it's going to match them. And if it is not this particular machine, it's going to drop it. And now if you try to access this particular machine, it's going to assign a different port number. So whatever discovery you did is going to be completely useless. So that makes it so hard. Port prediction is going to be very hard for symmetric NATs. Questions here?
I was wondering what kind of NATs, can you hear me?
Yes, yes.
Oh, I was wondering what kind of NATs because actually it is used in some, like, because I like gaming and they actually use that in the like Xbox One, I heard, and all of the other like online stuff.
Yes.
Is it used there somehow, or which one is the best?
Yeah, you should definitely try to avoid symmetric NATs. For example, most of the enterprise routers, like Cisco routers and all that, they use symmetric NATs and they make your life really hard. So many of the other home routers, they don't use symmetric NATs. They mostly use port restricted cone NATs. So they are fine. You can use them. So like Netlink and many of those other companies. In Ubiquiti, I think, for example, probably maybe using symmetric NAT. Some of those enterprise lines of them, product lines may be using symmetric NATs. But if you choose any of the non-enterprise home router segment, you are most likely to be fine. But yeah, it makes gaming so hard. It also makes voice over IP so hard. You'll have to use some of these relay. Voice over IP is very hard because it needs to open a lot of ports. you have RTP port, there is RTCP port, and for receive you have another port, and it's so complicated. And each of these opening of the port will require these kind of hole punching, and if it uses symmetric NAT, then you're totally in trouble.
And which one of these variations do you think is the most secure one? Or is it also enough for these to be used? Like, are they actually enough for security reasons, or are they like coupled with other?
Yeah, they are coupled with other things as well in certain routers. So for example, some of these routers also rewrite any IP looking payload. So let's say if you're carrying a payload in one of these packets, and if those payloads also are themselves another IP packet, for example, like you may have overlay networks in some of these overlay networks in data center computing, or if you're familiar with the Linux has this tap devices. You can tunnel one IP connection within another IP connection. That is, you can put one IP packet as a payload for another IP packet.
So it's IPception.
Yeah, exactly. Yes.
Like the movie Inception.
Yeah, yes. So so some of these data center networking, they use those kind of things to implement their own networking on top of the regular internet. So so what these sort of routers do is they rewrite anything that looks like an address, even in the payload. So they do deep packet inspection and sort of rewrite all these packets, and that would make things so hard. So you'll have to resort to other things like encryption. You completely encrypt your packet, and it goes out so that the router has no way to really identify your payload.
Okay, thank you. I was actually also have one other question. Actually, just a second.
Yes,
I took a note of the first protocol that the magic wormhole. The magic wormhole. And does it actually incorporate one of these, or is it like actually that has nothing to do?
Right now it does not. Right now it incorporates a very simple form of a NAT traversal, but a full-fledged form of NAT traversal is still being talked about. There is an issue on GitHub opened. Of course, you are also free to contribute or look at that issue. And if you want to take a more deeper look into that, I can post the issue number into the Keybase.
Do I need like a full a lot of like I am actually a developer, but I don't know if I need a lot of networking knowledge, right?
No, don't worry about that. Some of us can help you along to do that, so don't worry at all about that. You don't really need a lot of networking knowledge. Mostly understanding of these concepts is probably most important there. So you can definitely contribute.
Yeah, thank you very much. Thank you.
I'll post these. Make a note of these and post these on the chat channel. Like if not today, tomorrow morning.
Fantastic.
All right. Thank you.
Ram, we're running a little short on time, but I encourage you to complete whatever you had prepared as well, just only as a heads up that some people may be dropping off the call.
Okay. I'll just skip some of these because I think we have already talked verbally about these. So one of these is the hole punching technique is to have some sort of an introducer outside the network, and say that is on the public internet. So you talk to that particular machine first and ask that machine, can you tell me what my public IP and public address is? Like you might have seen, what is my IP.com? And if you type what is my IP into Google, it will say some IP address. That is usually your public IP address, not your private IP address. So there are services that you can run on the internet that will allow you to find out your IP address and port pair, and that that you can pass to the other party and the other peer that you want to talk to, and they can try to send packets to you. So that is the thing that we want to discuss now. So there are 3 different scenarios. I think I'll try to discuss at least the first 2 because it's already quite late, I guess. So I have few slides, but I think these 2 probably I'll try to go in detail. Maybe 10 more minutes. Is that fine, Angie? But I think if other people have other things to do, it's already
That's
late
fine
there.
for me. Yeah, and people
Okay.
can stick on if they can stick on.
Yeah, I can. I'll be definitely posting these slides to you, Angie, and then you can also distribute to others. So, and they can come back and also see the recordings if they drop off. But I'll try to go through these 2 in detail so that they can easily understand the third case and rest of it. So this is the simplest case. You have before we do hole punching, let's say that both of us, both the peers are in the same network, say within an office, say I and Angie are working for an organization, same organization. We want to send a file to each other. So client A is Angie and client B is me, for example, and there is a NAT router sitting in the office. Now, we don't really know that client B is also in the same office. So we take the help of an external server. So we know that there is an external server sitting somewhere on the internet, and we take the help of this particular machine. It's generally called a rendezvous machine or an introducer. And we ask this machine, we send this first request to this machine and say that, oh, my IP address, as far as I know, is 10.0.0.1, and I'm talking to you from port number 4321. And it will send that packet to this particular IP address. And that request, it's going to send it to 18.181.0.31. That's the public IP address. So what this server does is, it will look at the packet's sending address. So every packet has a send and a source and a destination. So it can inspect the source address and see that. So what it will see is that the packet went through this NAT in order to reach this server. So this NAT is going to rewrite every outgoing packet. The source address is going to be rewritten with this particular address. The source address would magically become, instead of 10.0.0.1, it's going to become 155.99.25.11. And now that's what this server is going to see. But in the payload, we are going to say that, oh, my local IP address is this. Payload is going to just keep it untouched. It's only going to rewrite the source address of this packet, this NAT. So server is going to get both the public IP address because it's looking at the source part of the packet. And if it looks at the payload, it's going to get the private IP address of this packet. Similarly, the client B is also going to do the same. So the server S knows both the private IP address and the public IP address of both these clients. Now, as a second step, client A can request the server S, please let me know the IP addresses of the B that you know. And B would also say that, please give me the all known addresses of client A. So both of them are going to get these 2 addresses. The first address is the private IP address, 10.0.0.1, and the other one is 155.99.25.1, and the port numbers.
A super practical and maybe stupid question, Ram, but how does
no problem.
client A know that client B exists? Like, how do we know which one we're looking for? How do we know which address that we're actually looking for?
how do we know? Okay, so that has to be some protocol outside this. So for example, you can give a name, for example, like let's say you have a Skype call, for example, Angie at monadic.xyz. So that particular name you register at some address, right? Similarly, I may also register my IP address. So whenever this machine comes up, so I know that I need to talk to Angie. So I have some other mechanism like your name, for example, or some ID. So that is what I'm looking up here.
Got it.
So whenever these programs come up, like when you boot your machine or start that program, this is going to happen transparently. It's going to send a packet to this particular service and say that, oh, this is my IP address, and please note down this private and public IP addresses. Similarly, this also is going to do that. So a server is going to learn about both these addresses of both the parties. And now I say that, oh, I want to talk to Angie, and it's going to return to me both these addresses, like your private IP address and the public IP address, IP and port pair.
Got it. Thank you.
Yeah. Now what we do is we try to make a connection to both of these addresses. Both the parties, the client A and the client B, are both going to try to make a connection. Now, what would happen is that even though, so one of them is through this NAT, the public IP address of both of them are 155.99.22.25.11, and the port numbers are different, but so this particular client and this particular client, they are simultaneously going to try to make connections to each of these addresses. They are going to send packets. So this particular one, this particular attempt is one, this particular attempt is another one through this NAT, because there are two IP address pairs, one public and one private. So this is going to succeed immediately because now they are both in the same network. So this is going to succeed. And so whichever succeeds first, you would just grab that and drop all the further connections. And now this is going to succeed. And now they have discovered that this peer has discovered this peer. And now without going through any of these network, it's going to talk to each other. So now this session is established. And this is going to be the session AB. It's just not going to need any of these. It doesn't need a server. It doesn't need NAT or anything for the further communication. So a hole has been punched. Not really a hole. It's not really going through the NAT. We just know each other. We just discovered each other, and we just carry on conversation directly peer-to-peer. This is the simplest case. Now, now this is the second case where, say, I am sitting here, Angie is in a different network in her office. So I'm going to talk to Angie through this. So there is a NAT connection there. Angie has a router in the office. I have a home router here. So there is a service again like this. So whenever your peer-to-peer program comes up, it's going to talk to the server and say that same procedure as before. It's going to say in the payload that, oh, my IP address is this. I'm going to talk to this machine. Now that packet, the source address of that gets rewritten with this NAT public IP address. So whenever the packet arrives here, this address is going to be only in the payload. The source address is going to get rewritten with some other address, this address. So the server learns both this particular address and the private IP address. Similarly, this node is also going to do the same thing, and it learns these two. Now comes the fun part. Both of these clients are going to attempt Now, both A and B ask for the peers' IP addresses. So it's going to ask, server, please give me the IP addresses that you know of client B. And B is also going to do the same for A. So server S gives them the all the IP address and port pair that it knows about. So it gives them these two addresses and it gives these two addresses to A. Now what A and B is going to do is it is going to try to attempt a connection to all these addresses. So A is going to send a packet to B's private IP address and the public IP address. So let's take the private IP address. So it's going to send a packet to 10.1.1.3. And that address does not make any sense. That would go to one of the machines on the same network. So if there is a machine with the same address, and if that machine is also listening on the same port, bad luck. That's going to go to that machine, and that could be a malicious machine probably, and it's going to receive all the packets. That's really bad idea. So something that you need to take care in your application is you need to have some sort of cryptography in the higher layers, like a sequence number or a nonce. Nonce is this random number that you may use, like it's a use only once type of thing. Never use more than once. That is what nonce. So you need to use some sort of a sequence numbering scheme in the packet and encrypt it so that so you need to have some application level protocol when you send these discovery packets and ways to handshake packets and you send to each other before you actually send these actual data. These are really handshakes that you have to negotiate and find the other peer. So this would go to another host on this machine. So this is just going to fail. Similarly, for client B, it's going to send a packet to 10.0.0.1 that is not going to go anywhere because this NAT is a separate network and this NAT is a separate network. It's not going to go. So this machine would try to route it to another machine if that exists. If else, it's going to just drop it. But now there is another connection that we are going to attempt. We are going to send a packet to the public, this public address of B, which is 138.76.29.7 and this port number, which is nothing but this NAT's public IP address. Because remember, when the packet went out to server S, this NAT rewrote the source address of that packet. So this is what the server learned, and the server thinks that that is the public address of this client B. So A is going to send a packet to this public address and public IP and public port. So it will pass through this, it will make an outward connection. So a table entry gets made here that, oh, and there is an outward connection being made. Now, similarly, B would also do a simultaneous connection attempt to A's public IP address, which is 155.99.25.1. I hope this slide is visible properly. Now, if A's packet, so now these are being simultaneously made, but there may be a few milliseconds of delay because of network hops or any such thing when these packets arrive. So if this packet arrives here, A's packet arrived at B's NAT before this packet has gone out, before the B makes a connection attempt, this is going to get dropped here. But at the same time, if this packet went out here, we have already made an outgoing connection. So a table entry has been made here. This NAT router is going to think that this packet that arrived, the connection attempt that arrived, is a reply to the entry that we have already made. So this packet is going to be let in as this NAT thinks that, oh, this is the packet that I really want. because this is the reply that has come for the session initiation that this particular client initiated. So it is going to let it in, and this is going to succeed. So finally, this packet will make it to client A. Now, since this outward connection was made, the further packet request to B is also going to succeed from A, because this outward connection has already been made. Now all the further connections to B is going to succeed. So a session like this will get established. So client A, it goes to NAT, then it goes to this particular NAT, and it is going to succeed. So you have a peer-to-peer connection without the use of server S. So it will still go through the internet, but not through many hops. You can still think of it as some sort of a peer-to-peer connection. It's not direct peer-to-peer like this, because that's not possible. They are not directly on the internet, but it is sort of like that, because these two are on the internet and they are sort of talking to each other. You have just one additional hop. Is this clear?
It was clear to me, yeah.
Okay, nice. Thanks.
Really, no, well explained, Ram. No, that's good on my part.
Okay. Anybody else, if you have any questions? So this one is like a multi-level NAT, which is like a further extension of this. And I think in the interest of time, we have shot already more than 15 minutes. So I would just skip this. That's just an extension of the previous slide. So, yeah, I would request you to go through this at your time later and just come back if you have any question. There's just an extension of this at a multi-level NAT, like an ISP level or multiple levels of NAT. So now we talked about the server, right, sitting here. Rest of the things are all standardization of these machinery. So you need to standardize what are the messages that is going out from client A to server and client A to client B. Is like peer-to-peer messaging, peer-to-server messaging. And the case of symmetric NAT, remember we discussed the symmetric NAT where random port number gets assigned. This hole punching is not going to work there. So in that case, we need an external relay. So there is a standard for that. There is an RFC called traversal using relays around NAT called turn. It is called turn. There is an RFC for it. So there is a RFC is just nothing but standards and messages for how to talk to the turn server and how to relay a file or a message. The server that we talked about, the rendezvous server, the server S, that's called a stun server. Stun stands for session traversal utilities for NAT, and that's specified in this RFC 5389, and that talks about the server messages to discover the transport addresses. And recently, there is this thing called WebRTC that has been built into the browsers, like a couple of years ago. Some of these browser makers like Mozilla and Google and Microsoft, they all collaborated and put all these things together into the browser so that a browser itself can talk to another browser and make voice calls or send files. And they have come out with some messages on top of these two things. These are just nothing but messages on top of stun and the turn relay system, and they call it as interactive connectivity establishment. They're really these messages. First sending this message and then sending these messages, basically the messages between the already discovered addresses. So those are those interactive connectivity, like finding the candidates, the possible candidates, and those kind of talking to stun and turn. It sort of enhances the stun and turn protocol with some additional messages. So these are really useful for if you're doing P2P, any P2P programming or P2P products, if you're writing things on your own, these are definitely the things that you will be using again and again. There are some other techniques like universal plug and play, and these are sort of proprietary things. UPnP is not a proprietary thing, but there are very few routers that really implement the UPnP. There is Apple's own standard called PMP, NAT PMP. That is also like only implemented by Apple routers and not much by any other routers. So that's not very popular. So we are sort of stuck with these soup of standards to implement any P2P service. Like there are so many RFCs to read and understand. So that's the thing. So symmetric NAT is the main challenge. Similarly, think about it. Like say if you have two peers and they want to talk to each other, you are going to take some time before you discover all these public IP and public port and private IP and try to attempt connections. All these are going to take some time. So before you can actually do your work, like initiate a voice call or send a file, you are going to spend a lot of time trying to initiate connections. And network connections are always troublesome because there may be timeouts. You might want to keep timeouts very low so that you can try out different candidates. If that doesn't work out, try different candidates and things like that. The best, you might want to try all these connections in parallel and choose the first one that succeeds, and then do rest of the communications on that particular socket or the particular channel that you have opened. So yeah, that's all I have.
Thank you so much, Ram. We all really appreciate it. We did ask you a fair amount of questions throughout, but I'm sure it sounds like there might be some follow-up questions on Keybase and people who want to dig a bit deeper. So it would be great to continue the conversation there. But thank you so much for taking your time and for staying up so late. We really appreciate this.
No problem. No problem.